All right, maybe we can get started. And yeah, welcome back for week number 5 for the Quantitative Geology course. This week we are taking maybe a slight deviation from the theme of some of the other topics we've discussed. Not so much that we're going to talk about something that's not related to an equation, but more so that we have a topic that's not directly related to thermal chronology in this week's exercise. And what we will be talking about, if I can refresh the page and get lesson 5 to show up, is about viscous flow and the equations we can use to model things like the viscous flow for the exercise applied to ice. But we'll see in the kind of introductory lecture some examples of also how viscous flow relates to rock inside the earth. And so it's a useful thing to see. I think it's kind of a interesting topic in general, but there's not a direct connection to thermal chronology. So I've still a bit, haven't been able to figure out how to get this one to fit into the theme as nicely as the other exercises do. But the good news is that we'll still use some of the functions that we created in the earlier exercises in this week's exercise, so you still kind of get the idea of why it's nice to have a library of functions, even though our topic is a little bit different this week. So overall, the plan basically is to have a short-ish introductory lecture just to talk about how we can model the viscous flow of rock or ice, and then we'll take a look at a couple different examples of some theory stuff that's on the course page that you could basically just have in mind to refer to for the exercise for this week, and then as usual we'll wrap up with a preview of exercise number 5. Perhaps before we get started, are there any questions or comments or issues that have come up in the last week? So, all right, well, I'm not seeing much there. For those who replied in Discord, thanks for making it clear that you're active in the course, and I'll try to update things in Sisu in the next couple days, so for those of you who had their registration rejected or whatever, I should be able to fix that soon. And if you haven't said anything yet in the Discord about being active in the course, please do that as soon as possible. But yeah, let's then get on to our first kind of activity for today, which is to go through some slides about rocks and ice as viscous materials. And our goal here is basically to introduce the kind of framework of understanding viscous flow of rock or ice, and then to look at some different end member types of viscous flow in a channel. What we're going to end up doing in the exercise for this week is essentially looking at velocities of ice flowing down a glacier that's bounded by the walls of a valley, which is essentially kind of a channel flow type of system. So it's useful to see what the different end member channel flow models are, and then we'll talk a little bit about the effects. Not really too much about temperature on viscosity, but we'll talk about the nonlinear behavior of rock when it's flowing. But to give you a couple examples, of course, we can consider something like an alpine glacier, which is more or less flowing downhill as a result of gravity acting on the mass of ice that is the glacier itself. So this is an example of a glacier from Alaska in the US. I don't know where the photo came from. Probably some kind of free online public domain photo bank. But what you can see in this case is ice that's basically flowing down to sea level. And the driving force for that motion is typically a combination of some sliding along the base, depending on the temperature, and a few other factors. The ice may be sliding along its base, but it's internally deforming and flowing. That's one of the main mechanisms under which this ice is accumulating at high elevations and flowing down, in this case, to sea level, where it's probably breaking off into pieces and then drifting off and slowly melting in the sea here. Another example of viscous flow is what follows glacial loading in places like this. So when you've loaded the surface of the Earth with something like an ice sheet, it of course causes some subsidence, and the subsidence that occurs basically displaces the asthenosphere that is below the lithosphere due to the load of ice. And so at the end of a glacial period, when the ice load melts away, essentially you have a surface that's been depressed as a result of the glacial loading that slowly starts to move back up into its equilibrium position based on sort of a full rebound and returning to an isostatic equilibrium state. That's kind of shown in cartoon form here over on the left, where you can see an ice sheet being placed on the surface, the substance that occurs deflecting the surface downward, and actually warping upwards on the sides usually of where the ice load has been placed. Once it's melted away, you have that depression, and the rebound that occurs takes on the order of thousands to tens of thousands of years to occur, because it is limited by the rate at which the asthenosphere can flow underneath the lithosphere. So that's kind of preventing it from reaching an isostatic equilibrium much more quickly, because you're limited by the velocity due to the viscous nature of the asthenosphere. Yeah, Thoughtful.
Can we determine the sort of low rate of the asthenosphere from the upward motion of the thrust?
Yeah, I mean, in essence, that's one of the ways in which we've been able to estimate what the viscosity of the asthenosphere would be, was from the rate of rebound. Okay. So you can kind of calculate that based on, there's various assumptions you can make about how you want to do the math there, but essentially you're able to back out what the viscosity would be if it's rebounding by this much over so much time. You can calculate that. So that is one of the ways in which, I mean, because the asthenosphere is largely not accessible directly, that's one of the ways in which we've been able to estimate its viscosity. So yeah, good question. And then over on the right's a paper I just found. I had some old picture from like 2012 from the Helsinki Sanomat of like some contour map showing rebound velocities in the Bothnian Bay, and I felt like it was getting a little bit, I don't know, too far out of date to be interesting. So I came across a paper that was published earlier this year using, in this case, I think they were using some kind of geodetic measurements to try to look at the competition between sea level rise and the rebound of the land surface in different parts of Finland. So like obviously in Vaasa, you're on the sort of Gulf of Bothnia, or close to the Gulf of Bothnia, where you have this sort of among the fastest rates of rebound of the surface from the post-glacial isostatic adjustment. And then here in Helsinki, you've got a much lower rate of land surface uplift. And the forecast would then be that depending on what assumptions you make and which models you use, that the expectation would be that the kind of relative sea level would be going up in the next roughly 80 years in most cases in Helsinki. Perhaps not going up a substantial amount, but the expectation would be there'd be some sea level rise here. But in Vaasa, the thought would be that the sea level or relative sea level would either be similar to what it is today or possibly even slightly lower than it is today, because the land surface is rising faster than the sea level rise due to melting of ice. So if you're curious, you can find the full citation to the article at the end of the slides, which I'll put on the course page. But it just seemed like kind of an interesting example showing that this glacial isostatic adjustment, a big concern in a lot of places is how sea level rise is going to affect things. And if you live in Vaasa, perhaps you're not too worried about it, at least for the next 80 years. Of course, after that, once, this kind of rebound is an exponential decay function, so it's slowing down all the time. So there could be a point at which this then starts to become more problematic. But anyway, just thought you might be interested to see that there are people looking at exactly this problem, even quite recently. But yeah, if we want to talk about viscous flow, we have to first talk about a fluid, because we are going to consider whatever this material is that's flowing to be a fluid. And the definition that we can give basically is that we have any material that flows in response to an applied stress would be considered a fluid. So for instance, if I push on this table, the table basically doesn't move, at least not in any kind of appreciable way, and that's because it's not behaving like a fluid. So if by contrast just happen to have the little bottle of whatever hand sanitizer here, anytime I change the orientation of the bottle, it's causing the fluid to flow around in there because I'm applying stress by rotating the bottle, and that stress then causes the fluid to flow in response. In this case, it's also flowing because it's trying to reach an equilibrium with the acceleration due to gravity to kind of keep a flat surface on the top of the fluid. But anyway, you get the idea. With fluids, deformation is continuous, so it's not going to be sort of fault-like where you have discrete zones of deformation and then much of the rock that's not deforming, but instead the whole fluid is likely to be deforming when it's deformed. And the sort of relationship that we have mathematically is that the shear stress or the stress in the fluid is proportional to the rate at which it's being deformed. So this du dz, u would be some kind of velocity term, dz would be then some distance, and so then this is a velocity gradient as a result. And then there's the proportionality between the stress and the velocity gradient. That's essentially the definition of what we could call a fluid. Now, the proportionality constant that allows us to go from saying things are proportional between stress and the velocity gradient and being equal to some term times the velocity gradient is called the dynamic viscosity, which is most often just referred to as viscosity. So this is then the Greek letter eta that's used, although there are several others that can be used for viscosity as well. I use eta. And in one dimension, then we can say that our stress in the fluid is simply the viscosity times the velocity gradient. So what that means is that as the velocity gradient goes up, so the more you deform or more rapidly you deform the fluid, the higher the stress would be, and similarly, the higher the viscosity is, the larger the stress is in the fluid for the same velocity gradient. Basically, for viscosity, you can think about this as resistance to flow, and so there's this little animation here on the left side showing a low viscosity, something like water, that's very easily flowing, and then a higher viscosity fluid, maybe something kind of like softis or toothpaste, that is then flowing more slowly. So it's kind of oozing into a flat surface over time, whereas this water quickly forms a flat surface and it sloshes around a little bit because it's able to flow more easily. But the higher the viscosity is, the more resistance it is to flowing. And there's a couple other terms here, kinematic viscosity and bulk viscosity. Bulk viscosity is kind of a measure of the volumetric change of the material, and those are not the same as dynamic viscosity, just for the sake of completeness. In terms of viscosities of common materials you might be familiar with, we can treat air as a viscous fluid. I mean, you might not really feel like it, and you can easily move your hands through the air and you hardly feel any resistance at all. And that's because it has a very low viscosity, on the order of 10 to the minus 5 Pascal seconds. So that's the typical viscosity unit. Water, by contrast, has a viscosity around 10 to the minus 3. So 2 orders of magnitude higher. And of course, if you move your hands through the air and you can feel that, you can imagine if you're doing the same thing in the water, there's much more resistance to your motion when you're moving your hands through the water. And if you imagine immersing yourself in a bathtub full of honey or something like that, again, now you've got 4 orders of magnitude difference in the viscosity. It's much harder to move your hands through honey at the same speed as you could in water or air. And of course, that's a weird example to envision, but you get the point that this is how these viscosities can change. And they vary over a huge number of orders of magnitude. So from air at 10 to the minus 5 to granite at 10 to the 20, there are a massive number of, or massive range of viscosities of different materials. And if we look somewhere in the middle, ice has a viscosity around 10 to the 10 Pascal seconds. We can actually measure and watch glaciers deforming in real time. It might not be that you can sit there and watch right before your eyes the ice flowing, but if you make measurements over a period of weeks or even months, you can see appreciable distances that the ice has deformed and flowed. Not so much the case for granite, especially at surface temperatures. But the point is that when you heat these materials up a little bit and they start to become more viscous in how they're deforming, that you do have also viscosities that you can associate to these rock-like materials. So whether it's rock salt or granite, that are going to be flowing more slowly, but still behave basically like a fluid over geological timescales. And this is the whole idea with mantle convection, is that it occurs in the solid state, but the motion over geological timescale, so tens of millions of years, is like that of a fluid. The mantle convection is something that's taking place very slowly, but it's nonetheless happening in a fluid-like manner. Yeah, viscosity goes down. They become less viscous when you heat them generally. I don't know of any material that I can think of right off the top of my head that would become more viscous with being heated, unless it changed into like some other kind of state. Like if you, I don't know, evaporate the water out of something, it may become more viscous as a result of losing water. But yeah, I mean, the tendency for me, at least in how I think about it, is that as you get higher temperature, your viscosity is dropping off. So these are like reference viscosities for materials at approximately room temperature. The higher the viscosity is, the more resistant it is to flow, and generally that's the inverse of the temperature relationship. The higher the temperature is, the more easily it flows, which means its viscosity is going down. Yeah. So, yeah, I mean, like this example of, whether it's something like water and, toothpaste or whatever, is two different fluids. But you could have the same kind of example where you just change the temperature, and this could be kind of colder in the lower case and hotter in the upper case because of this temperature relationship that we'll see in a little bit more detail coming up. But like honey's a good example, because if you take honey, I still remember, I think one of the first years I taught this course, one student told me they kept their honey in the refrigerator, and I was kind of surprised by this. But if you keep honey in the refrigerator, I mean, it does flow more slowly. So if you want to kind of like take some honey and scoop it out, you're going to have to push in harder with a spoon to get some like out of the jar or whatever, compared to keeping it at room temperature. And that is exactly that effective temperature on the viscosity of the fluid. So, yeah, anyway, and yeah, the reason why this sort of honey dipper works is because you can dunk it in the honey and get it out fast enough that the honey doesn't run off the dipper first before you go and like drizzle it on your biscuit or whatever's happening here. So we can talk about viscosity in a couple different ways. One is that we have a fluid that is having a Newtonian or linear viscosity, which means that the relationship between stress and the viscosity is linear. So there's no kind of power law or exponent between these two things here. And in essence, that means that the viscosity has a constant value, which doesn't depend on the state of stress or the flow velocity. In terms of fluids, air, water, and thin motor oil are practically Newtonian fluids. Rock salt is sort of like a Newtonian fluid in the way that it performs, but most rocks are not actually behaving in this Newtonian way. So this is something that's kind of useful to know about as a theoretical model, but it doesn't necessarily represent rock that well. But nonetheless, we can use this sort of simplified case to look a little bit at some examples of how viscous fluids flow in, for example, a channel. And in this case, we have a diagram here that's showing two kind of bounding walls with a fluid between them, and this could be ice flowing down between the valley walls and the glacier, or it could be something like magma that's flowing through some kind of tube in the subsurface. But we can come up with a couple end-member behaviors of this fluid flow based on some assumptions we make about the fluid itself. So the first case is we can assume that in our scenario here, the velocity at either one of the walls of this channel is it's either 0, which we assume to be the case at the base, or equal to this U0 value, which we assume at the top. In other words, the fluid sticks to the wall. So if the wall isn't moving, the fluid's not moving at that contact point. Now, of course, it could be moving within here, but we're assuming that the two are coupled at the boundaries of the channel, in which case we can come up with a relationship like this. I think we'd cover this in the geodynamics course if you want to know where this comes from. But for our purposes, we're just going to say this is our velocity equation. And in here, there's a couple things to note. So you can see this U0 term that comes in, which is the velocity of the upper, or whatever the other wall of the channel. And then there's a dpdx term in here that's a pressure term. So in order to get the fluid to move, we have to apply some stress. The stress could come either from the wall of the channel moving, or it could come from a pressure that's being applied to the fluid that's different on either end of this channel, which would cause then the fluid to flow down the channel. In the first case, if we assume that there's no pressure gradient and we move one of the channel walls, what we end up with is what's called couette flow, in which case the fluid basically just has a linear increase in its velocity from one channel wall to the other. So it's behaving kind of just like a shearing of the fluid that causes it to move, such that nothing happens on the bottom, and you just have an increase in velocity as you go from the bottom to the top of this channel. This won't be something we really explore in our example today, but could be something that would apply to certain kind of faulting scenarios. Like sometimes people refer to this margin or the kind of bounding zone between two plates in the subduction zone as the subduction channel. And the subduction channel is a case where you have velocities that are different because one plate's going down, the other plate's either stationary or moving up, and that shearing can cause this type of motion of material that's within the subduction channel. But it doesn't really apply so often to cases like what we're looking at with ice in this week's exercise. But yeah, here we have something driven by movement of the wall of the channel with no pressure gradient. And of course we can solve for this. Doesn't really matter for our purposes, so I'm just going to skip that. So the other case, this sort of poissoidal flow, is what occurs when you have the two walls of the channel stationary and you have a pressure gradient that's driving the fluid to flow. So the pressure gradient in this case is higher pressure on, I guess looking at the screen, the right side, lower pressure on the left. And that forms then this kind of parabolic shaped velocity profile so that you get a maximum velocity in the middle of the channel, and then it sort of follows this parabola-like shape going to 0 at the two channel walls. So in this scenario, we're assuming we have a pressure gradient and no velocity applied to either of the channel walls. Again, you can get a different velocity solution here, and this looks more like what we'll see in this week's exercise, because essentially the gravitational force driving a glacier to flow downhill is like a pressure gradient. You have a sort of higher potential energy at higher elevation, and that causes pressure within the fluid that causes the fluid to flow down through some channel, in that case being bounded by the walls of some valley. So there's an example on the course page of how this can also be applied to salt tectonics. I think probably we don't talk about salt tectonics in any of the courses here. Maybe somewhere salt tectonics comes up, but it's a little bit of an obscure topic. But it relates to places where you have layers of salt that have been deposited, often in like an ocean basin, and you have deposition of sediment on top of the salt. That pressure of the sediment causes the salt to get displaced and flow out. And it's usually of interest because oftentimes there's connections between these salt diapirs and oil and gas that gets trapped next to them. So I was living in Nova Scotia in Canada. A lot of the oil and gas exploration that was taking place there was related to salt diapirs. Same in the Gulf of Mexico, off the sort of coast of the U.S., where this kind of salt tectonics is a bit of a big deal because there's a lot of money if you can find the oil that's trapped next to these salt bodies. Oil doesn't really like to flow through the salt very well. It's a pretty good sort of boundary so that you get things trapped within some kind of sedimentary layer that's pinned against the salt and then you've got a potential reservoir. So anyway, on the course page, if you're curious, there's an example of a paper. It's now almost 20 years old, but it shows the kind of idea of how this sediment loading causes salt movement and different types of flow in within a channel for, in this case, it was like loading offshore from some delta system. A couple other things to think about with our fluid. So we have some idea of how it flows inside of a channel, and we can talk now a little bit about why this linear behavior of the viscosity is not something that usually is applied to rock. And one of the reasons for this is that we have this dependency that's quite strong on temperature for most rocks. So as you go to higher temperature and the viscosity decreases, you can represent that in an equation that looks more or less like this, where there's a couple material constants here. So this is like a viscosity pre-exponent. That's a material property. Activation energy is also another material property of the, depends on what kind of rock you're deforming. And then here's the gas constant and then temperature. So you have this exponential kind of 1/T behavior, which results in a decreasing viscosity as temperature goes up. And so that's a kind of expectation for geological materials and many materials, honestly, that there's a strong temperature dependence in terms of the viscosity. You can see this, for example, if you look at the viscous strength of quartz as a function of depth, because as you go deeper in the earth, for the most part, temperature is going up, and that leads to this exponential decrease in the viscosity as you go deeper down. And yeah, that's quite clear when you start looking at the mechanical behavior of different layers of the earth in the crust and mantle, for example, that you see this kind of behavior manifest itself. And, well, I think I'll skip over this question at the moment. The thing is that that's not the only reason that we have this nonlinear type of behavior when we deform rocks. And one of the other things is that we see there is this power law dependence of the stress for most rock-like material when you deform it. So typically what you see is that when you double the force you apply to the rock, you get about 8 times in the sort of rate of deformation. So if we increase this stress tau that's acting on our fluid by some factor of 2, then what we tend to see is that this rate, this velocity gradient, would go up by a factor of 8, which reflects the fact that this power law exponent is somewhere typically between 2 and 4. And if it was a value of 3, 2 to the 3 would give you a value of 8, which is roughly what you see in terms of the rate of deformation. So that's another mechanical thing that has to do with the way in which the rock is being deformed. And that means that the shear stress and strain rate, or du dz term, are not linearly related to one another, but have this power law behavior. So in the exercise for this week, we're going to look at modeling ice flowing down a channel, and we're going to change the power law exponent to see how it changes the velocity you see in the ice that's flowing down a channel or flowing down some kind of inclined plane. Now, this pre-exponent thing that's similar, it's another material constant, it's A effective, but it has funny units on it that it's pascals to the n seconds because it is this shear stress. So this would be sigma, this sort of shear stress to some power n, and then so you should have some power law exponent over here as well to get the units to work out. Because this is basically pascals is what would be your unit for stress, pascals to the n, and then this is going to be something per second. du dz is going to give you units of per second, so that cancels out the other one there, and that's how you get to this funny pascals to the n seconds. So maybe now we have some idea of how fluids are flowing and some of the things that drive them. We'll just have a couple slides here about glaciers, and then we'll get on to looking at some other things for this week's exercise. But probably you've seen at least some kind of figure like this about how glaciers are thought to flow, and that is that you have some zone of accumulation, essentially where snow is falling and sort of giving a positive mass flux to the glacier, and a zone of ablation where you have melting or other ways like calving away of the glacier that can take place, for instance, for these kind of tidewater glaciers that are hitting sea level, where you're losing mass. And so somewhere in between the area where you're gaining mass and you're losing mass is this equilibrium line. And essentially the idea is if you looked at the flow lines of things going through the glacier, that they kind of follow along parallel to the surface of the slope that the ice is flowing over. And this applies mostly to, in this case, kind of valley type of glaciers, or alpine glaciers. Whether or not it's sliding along the base will depend on whether you have a kind of cold-based or warm-based system, where warm-based would be then sliding along also in addition to the velocity of the material flowing through here. So in terms of how things move, of course, there's the already mentioned basal sliding and this internal deformation where the ice is basically just deforming due to the weight of itself and flowing like a nonlinear viscous fluid down to lower elevation. And this is sensitive to temperature, but we're not going to look at temperature as a factor in this week's exercise just because it gets a bit more complicated. But we'll explore basically just the effect of this nonlinear behavior with the power law exponent to see how that affects the profile of the velocity of your ice in the glacier. So what we're going to be doing basically is two different types of, I would say, models. One would be looking at ice flowing down some slope. And so in this case, we can calculate what's like a vertical velocity profile. So if you just kind of took a cross section through a glacier flowing down a slope and looked at what the velocities were, you'd see the velocity is either kind of 0 or equal to the sliding velocity at the bottom of the ice. And then as you go up from there toward the surface, you should see some kind of increasing velocity following a profile, for instance, something like this. And so then you can relate things like how steep the slope is and the forces that are acting on the ice to figure out how big this velocity would be in this case. What we're also going to look at is a sort of map view of, if you look down from above at a glacier where you have a valley on one side and a valley on the other and ice filling in between, what the velocity profile looks like going across in map view. So we'll also look at that, which is kind of like sitting at the top surface and just looking at like the third dimension now of what happens to the velocities here as you get close to the valley wall on either side. So we'll look at those two things as ways to kind of explore the velocity idea. You'll have to calculate what the velocities are, and then we'll play around with the power law exponent to see which one seems like it fits the flow behavior of ice the best. So quick recap. We talked about the idea of a fluid and what viscous flow is. In this case, it's going to be something that's commonly used to model the fluid-like behavior of rock and ice in a case where the deformation rate is proportional to the applied shear stress. May not be linearly proportional, but at least that proportionality is there. And we looked at these Couette and Poiseuille type channel flow behaviors, and this, at least the Poiseuille type, was what we will look at in the exercise for this week. And then finally, just talked about the idea of this nonlinearity in the velocities, either related to temperature or related to the power law exponent of the deformation of the material. That's the kind of intro stuff for this week and this week's exercise. Are there any questions? We're jumping around a little bit in terms of topics, but it's hopefully not too big of a leap. All right, if I don't see any questions, I'll just note again that on the last slide here, which will go up on the course page, if you want to check out the paper about this kind of competition between sea level rise and land surface uplift, you can find it here. It's open source or whatever, open access. So you should be able to get a copy of it without any problem. All right. Then let's have a look at what's up after this. So here, by the way, is that optional article about the salt tectonics, if you're curious. It's just on the same page with this rocks and ice as viscous materials, which is where the lecture slides will go when class is done. So just to set things up a little bit for the exercise for this week, there are 2 pages of things, or 2 web pages of stuff about viscous flow and theory that could be useful for this week's exercise. The first one about viscous flow down an incline is kind of an optional thing. All the equations you would need would be in this theory for exercise 5 part, but this kind of goes through a little bit of the math about how do you calculate what the sort of driving force is for a fluid that's on a plane, like figuring out what the difference in the potential energy is and how you connect that to a stress that's acting on the fluid. So I'm not going to go through this in detail other than just maybe to note that it's here, and if you're curious to see how you can, for instance, come up with what a velocity would be for a fluid flowing down a slope with some slope S, we can do that, and you can then, for instance, plot what the velocity of the fluid flowing down that slope would be. But this is mostly just, again, for reference, because I think at least for the exercise for this week, you don't necessarily need this part. But what you will more than likely need is the other part, this theory for exercise number 5. Again, you don't need everything that's here, but there's a couple equations that are going to be used in the exercise itself. So it might be nice that you can kind of see from start to finish how this works. So here's our example of a kind of looking down in map view on a glacier that's flowing between 2 walls that are fixed in terms of their velocity. And we're calculating then the velocity of the fluid that's within there between the 2 channel walls. So this goes through basically starting from the point where you want to calculate what the pressure gradient would be for the fluid as it's flowing down the channel, and then links that up to the shear stress, and you can then go forward from there to basically come up with an equation for the velocity of the fluid by integrating a couple times. And then you've got to solve for some constants here by making some assumptions about the boundary conditions, but ultimately you come up with a relationship that looks like this, that gives you the velocity of the fluid within the channel as a function of this pressure gradient, what position you're in, and the viscosity. The important things that you're going to deal with here is that this is the case for a linear or a Newtonian fluid, but of course for ice it's not a linear type of fluid. It's a nonlinear viscous fluid in terms of how it deforms. So the relationship you start from is a little bit different in that you have this tau to the power n, and what you'll end up using is this equation number 10 that's the same velocity relationship that you had before, but now it has a pressure gradient to some power n, and some of these other terms are raised to the power n plus 1. So you're going to be working with that equation number 10, I think, in the first part of the exercise. And then in part 2, you're going to work with a similar equation where we're dealing with ice flowing down an inclined plane. And actually, maybe this is in part 3 now that I think about it. But anyway, we have ice flowing down an inclined plane. So this is kind of like the cross-section view of the ice. And again, similarly, goes from like the starting point about what's the stress acting on the fluid and takes you through to equation number 19, which is where you get your velocity that you can use to calculate your fluid velocity from the bottom of the ice up to the surface. Most likely, we don't need to worry about the details of this now, but I'm guessing when you start working on the exercise, you may want to refer back to this to understand where some of the terms come from, and there may be some kind of useful things in here that would be a good idea to read this through before getting started on the exercise. Any questions at this point about the theory stuff? Okay. I would say if there's not any questions about this, maybe we can do a short break now, because what's left is essentially just a preview of the exercise, and I'll show you a couple things in Python that'll be useful for this week. But there's not too much left. You'll have, I think we'll be done early, and you'll have time if you want to get started even taking a look at the exercise. But let's take 5 minutes now. So I'll come back a couple minutes past 3, and we'll continue from there.